In the last lecture, we discussed electric lines of force and their properties. Their chief properties are that lines of force start at a positive charge and end at a negative charge. Then at any point on the line of force, the tangent at that point gives the electric field at that point. Third, the lines of force cannot cross each other, because if they do, then at that point where they cross, there will be two tangents and two directions of the electric field, which cannot be possible because of the superposition principle of electric fields. We also learnt the relationship between the electric field and the electric potential. Today, in this lecture, we shall proceed further with the relationship between the electric field and electric potential, and then introduce electric dipole. Electric dipole, as you know, is a very important concept not only in physics, but also in other areas of science. So, let us start with the relationship between the electric field and the potential. You remember this relation, E equal to minus d phi by dr, E equal to minus d phi by dr, that is, the electric field is equal to the negative of the derivative of the potential with respect to r. The magnitude of d phi from this equation is E dot dr, which is actually the work done when a unit positive test charge is moved a distance dr. You see, if I move a positive charge a distance dr against the electric field, then the work done is minus E dot dr. So, the potential difference between 2 points a distance dr apart is the work done in moving a unit positive charge from one point to the other against the electric field. Since the work is done when the positive charge moves against the field, there is decrease in its kinetic energy and increase in its potential energy. You see what I am saying? Here is a charge, positive charge, when it moves against the field, it has to do work, and therefore, its kinetic energy decreases. If the particle is moved from a distance r 2 to r 1, then the work done on it is d phi equal to integral of r 2 to r 1 E dot dr with a negative sign. And if you carry out this integral after substituting the value of E, which is 1 by 4 pi epsilon q by r squared r cap dot dr, then integrate and then we get q by 4 pi epsilon 0 1 by r 1 minus 1 by r 2. So, that is the potential difference between the points r 1 and r 2. The charge has moved from r 2 to r 1 against the electric field, and this is the work done. If we take r 2 to infinity, you remember that at infinity the potential is 0. You know, potential goes as q by r, and r at infinity potential is 0, 1 by r 2 goes to 0, and we get potential at a point r from the charge q, and that potential is q by 4 pi epsilon 0 times r. You see, this has vanished. R 1 I have redesignated as r. So, the potential becomes q by 4 pi epsilon 0 times r. Since charge is guided by the potential difference, it is the potential difference that is important, and since it is a potential difference, it does not matter where the 0 of the potential is taken. 0 of the potential can be fixed arbitrarily, because it is the potential difference that is important. And moreover, we can write phi equal to q by 4 pi epsilon 0 plus constant. When I say plus constant, actually I am fixing the value of 0 somewhere, because when I differentiate phi with respect to r, the derivative of constant becomes 0, and we get E equal to 4 pi epsilon 0 q by r squared times r cap. Since it is a difference of potential that is important, the 0 of potential can be fixed anywhere arbitrarily. And since phi is a scalar quantity, at a given point the potentials due to all the charges can be added up algebraically. That is, phi is equal to phi 1 plus phi 2 plus phi 3 plus phi 4, etc. If phi 3 is negative, then it is phi 1 plus phi 2 minus phi 3. So, we add them algebraically. A line over which potential is constant is known as equipotential line. Similarly, if there is a surface where the potential is constant everywhere, it is known as an equipotential surface. The important thing is that electric lines of force are always perpendicular to the equipotential lines and surfaces. As I have shown here, these are the equipotential surfaces, green, and the blue are the lines of force. They are always perpendicular to the equipotential surfaces. We just learnt that the potential phi is equal to q by 4 pi epsilon 0 r, and this measures the electric potential energy of a unit positive charge, because there is a work done on a unit positive charge. If the charge is that is moved is capital Q, then the potential energy is q times capital Q by 4 pi epsilon 0 r. Like the potential energy due to various sources can also be added algebraically, because energy is a scalar quantity, so it can be added algebraically. The change in potential energy of charge q when it is moved from point r2 to r1 is obviously qq by 4 pi epsilon 0 1 by r1 minus 1 by r2. Since electric field, like the gravitational field, is a conservative field, the change in the potential energy is independent of the path taken to go from r1 to r2. That is, if I take a charge from one point to another, whether I take it by this route, whether I take it by this route, whether I take it by this route, it does not matter. All that matters is that the potential energy difference is qq by 4 pi epsilon 0 1 by r1 minus 1 by r2. The route going from r2 to r1 does not matter. So, the potential energy difference between points r1 and r2 is qq by 4 pi epsilon 0 into 1 by r1 minus 1 by r2, and the change in potential energy is independent of the path from r2 to r1. Path can be any curve, but what matters is the difference in the potential energy. The path does not matter. Let us take an example to fix these ideas. Since E is minus d phi by dx and we are given E is constant along the x axis, uniform field along the x axis. So, what happens to phi? If I go from x1 to x2, then phi is simply minus Ex plus a constant, and this is a phi equal to minus Ex equal to constant is just a straight line, the green one here. So, if electric field is like this, uniform along x axis, then the potential due to this field is a line which is phi equal to minus Ex plus constant, and this constant can be made 0, and this line has slope equal to minus E. So, the electric field like this, but the potential is a straight line with a slope minus E. Take another example. Two identical particles each of mass m carrying a charge q are held at a distance r I. When they let go, find their velocities when the distance between them is r f. Initially they were at a distance r I, r initial, finally they are at a distance r f. So, we have to find the velocities. So, conservation of energy requires that the change in potential energy of the particles is equal to the kinetic energy, because there is no other energy sharing process. So, the kinetic energy goes into potential energy and vice versa. So, we have q by 4 pi epsilon 0 1 by r I minus 1 by r f, that is a change in the potential energy, and this must appear as kinetic energy. So, it is 2 into 1 by 2 mv squared, from which v can be calculated 2, because there are two charges, there are two particles carrying charge q, therefore 2 into half mv squared, from which if we know r I, r f, q, then we can find out v. Take another example. This is interesting, and examiners are very clever, you know. There are charges plus q and minus q here, and this C is the midpoint of this line AB, and D is at a distance which is equal to BC. So, BD is equal to BC. All these distances I have denoted by capital L. Now, what is the problem? The problem is charges q1 plus q and minus q are placed at distances a and b, at points a and b respectively, which are distances 2L apart. C is the midpoint. Show that the work done in moving a charge plus q along the semicircle CRD is minus QQ by 6 pi epsilon 0 times L. So, all that I have to find out is the work done, and I have just told you that the work done is equal to the difference of potential energy. The route does not matter. The route that the charge takes does not matter. So, in this case also this route does not matter. So, all that we do is we calculate the energy at C, then we calculate the energy at D. The difference of these two potential energies is equal to the change in the energy. This, whether it takes a semicircular path or a straight line path, does not matter. So, the work done is just the potential energy of Q at D minus its potential energy at C, potential energy at D minus the potential energy at C. We find the potential energy of Q at C, which is 0, then potential energy of Q at D. So, we take the difference of potential energies, and this is this. Therefore, the net work done is minus QQ by 6 pi epsilon 0 L. The path does not matter. Now, we introduce what is known as an electric dipole. You see, if you have two equal charges which are placed at a very short distance from each other, they form what is known as an electric dipole. An electric dipole is a very important concept, not only in physics, but also in other sciences. And the product of the charge, the magnitude of the charge and the distance between these two charges is called the dipole moment. The distance between the two we denote by 2a. We shall find that 2a is very convenient. So, the distance is 2a, q is the charge, and therefore, 2aq is the dipole moment. Why this 2aq is important? We shall see that if we study the interaction of the dipole with other fields, etc., then this quantity appears everywhere, 2aq, and that is why it is important and it is called dipole moment. So, these are the two charges. The line joining the two charges is called the axis of the dipole, and the dipole moment is a vector which is from minus q to plus q along the axis. Dipoles are important because a class of molecules have their negative and positive charges displaced by very short distances. Why it happens? We will see in a moment. These molecules are called polar molecules, and water is a good example of a polar molecule. How it comes about, we see in a moment. You see, here I have shown you the structure of the water molecule, atomic structure. You see, these are the hydrogen atoms, this is the oxygen atom, and they share these two green, shown in green, electrons. Now, what happens? The remaining electrons, these red ones, they exert force on these two shared electrons. These charges of the hydrogen atom also apply force on these two shared charges, but since the force due to these negative electrons is higher, there is a separation between the charges. So, negative charge on one side and positive charge on the other side, as I have shown here. So, it is a negative charge, the molecule becomes a dipole, there is a negative charge here, there is a positive charge here, and the distance between them is very short. So, it becomes a dipole, and such a molecule is known as a polar molecule, because there are two poles now, minus charge and plus charge, and that is how the water molecules join with one another to form chains. You see, this positive connects with this negative, this positive connects with this negative, this positive connects with this negative, and like that. And in this way, the chains of the water molecules are formed, which is a solution or water liquid. Let me give another example, which is not a polar molecule. We have carbon dioxide. You know, the 4 electrons of carbon are shared by the 2 oxygen atoms, and they are so symmetrically placed. Actually carbon dioxide is a linear molecule. They are so placed that the forces between charges on this side and on this side, they cancel, and therefore there is no displacement of charges from one another, and therefore this molecule is not a polar molecule, and the dipole moments cancel. You see the force or the moment between this and this and this and this, the dipole moments, they are in opposite direction, equal in magnitude, and therefore they cancel. This is a non-polar molecule. Let us now find the electric field due to a dipole. It is a very simple thing. You know what we do is, this is a positive charge, this is a negative charge. So, we find the field at the point P, and due to this negative charge we find the field at the point P, and then we compound the two fields, and this point P is on the equatorial line of the dipole, the line that divides the dipole into two equal parts, and it is perpendicular to the axis of the dipole. So, the field due to this charge plus q is in this direction, and the field due to this negative charge is in this direction, and if you break this into components, the what is left is the component shown here in this direction, parallel to this axis of the dipole, in fact anti-parallel. The axis of the dipole is like this is in this direction. So, this is parallel to the dipole, and the perpendicular components, they cancel, and we can find the magnitudes easily. There is no problem, because the distance is a square plus r square under root, and therefore we can find the electric field, and only the cos theta component survives. Therefore, E is 2 into 1 by 2 pi epsilon 0 q by a squared plus r squared under root the square of that. So, it is a square plus r square into cosine theta, and cosine theta we can write in terms, the cosine theta we can write in terms of the a by a squared plus r squared under root. So, it becomes 2 into 1 by 4 pi epsilon 0 q by a squared plus r squared into a by this. So, 2 AAQ, as I told you, this 2 AQ will occur very frequently, and that is known as the dipole moment. So, it is P by a squared plus r squared raised to power 3 by 2. And what is the direction? Direction of the field is anti-parallel to the axis of the dipole, and therefore, the field, if I give a proper sign etc., is given by minus 1 by 4 pi epsilon 0 p. P is a vector, you remember, the dipole moment is a vector. So, p by r cubed. So, that is the field, electric field in full form, in vectorial form, due to the dipole. Let us now find the field of the dipole at a point P, which is along the axis of the dipole. So, here again we have charge q, we find the field at P, we have charge minus q, we find the field at P, and then we add them and find the net field at the point P. So, the field due to plus q is 1 by 4 pi epsilon 0 r minus a squared. You see, this is a, and this distance is r, this distance is r minus a. So, E minus q is 1 by 4 pi epsilon 0 q by r plus a squared. We add them and we get the field, and that field is E plus q minus E minus q, because the field due to the positive charge is in this direction, the field due to the negative charge is in this direction. Therefore, we have to take the difference, and the difference is, if I give the, again I join 2 q a, it becomes P. So, all that has been done, and we get the field in the same direction, because this field is stronger. The net field is the same direction as the axis of the dipole moment. Therefore, we have E 1 by 4 pi epsilon 0 2 p by r cubed. At any arbitrary point, then what do we do is, we take the components of the dipole moment in this direction and in this direction. For this direction, this point is on the line bisecting the dipole. That is the first case. For this component, P lies along the line of the axis. So, we know since we have found the fields on a perpendicular line as well as along the axis of the dipole, we can use those results and add, and therefore, E axial is 1 by 4 pi epsilon 0 2 p cos theta by r cubed, because cos theta was the component. This component is cos theta times the component of the moment of the actual dipole, and on the equatorial line it is minus 1 by 4 pi epsilon 0 p by r cubed into sin theta, because this component is sin theta of the real or original dipole. So, we add them and we get just a little trigonometry. You can add and get E net is equal to 1 by 4 pi epsilon 0 p by r cubed 3 cos squared theta plus 1, and this field is along this line, the green line, and the direction is given by this angle theta. Tan alpha is E equatorial by E axial. E equatorial is this, E axial is this. So, it is the tan alpha is this, therefore, it is half tan theta. Tan theta is this angle, remember that. In this lecture, we did two important things. One, we found that the potential energy, when a charge moves from one place to another, the difference in potential energy is independent of the path. All that we have to do is to find the potential energy at one point, then at the other, and take the difference. The path does not matter. Then we introduced this concept of electric dipole, and we found the field due to this dipole at a point which is on the equatorial line and also at a point which is on the axial line, and then we generalize this to find the field at any point, because we can break the dipole moment into components perpendicular to, so that for one this is the equatorial line and for the other it is the axial line, and we add the two and get the result. In the next lecture, we shall continue with the dipole, electric dipole.